With my previous video I've released the Minimal 64x4, a DIY home computer with VGA and PS2 built out of logic chips. It's designed to be really accessible, easy to understand, and it runs at 8 MHz, packing 4 times the processing power of a Commodore 64. I've received quite a few questions like, how does it work and why is it so fast? The answer to the question comes in layers, ranging from I can turn it on and off, I can do useful stuff on it, I can build my own PC from parts, I can program it in, fill in your favorite high-level language here. Now if you continue watching this video, you'll be in for a deeper dive. What about, I know that processors execute machine code and I can code in assembly language. If you tick this box, you know that each processor type has its unique instruction set optimized for raw hardware speed, but not primarily for human readability. Still, assembly programming can be mastered without understanding how our machine executes instructions internally. We just need to know the result of each instruction. One layer below, we see that each instruction consists of a number of sequential steps called microsteps. A microstep uses and controls specific functional blocks of a CPU. So a basic understanding of these functional blocks becomes necessary, which brings us almost, but not quite in contact with the real hardware. Another level down we ask, how does each functional block perform its specific action? We need to look at the actual schematic of the digital circuits on logic level. Then, being familiar with the logic of the functional blocks, we look at the dynamics of the whole CPU system. How are the actions timed in the fastest possible way without messing up coordination? We are crossing into analog electronics here. And even deeper, we are concerned with transistors and other electrical components of our circuit. We are leaving our specific CPU design here and are drifting towards manufacturing processes. Today we omit layers 1 to 5 and jump straight into layer 6, assuming that you are familiar with assembly programming in general. You can take a look at the documentation of the Minimal 64x4 instruction set if you like, but it's not necessary to follow along. Let's begin by taking a look at the legend of the 64x4 block diagram. Functional blocks are shown in blue. Each block contains of subcomponents, shown in gray, with inputs and outputs. Their behavior is determined by so-called control signals, shown in red. It is a clean von Neumann architecture with components connecting to a single 8-bit data bus drawn as a black bold line in the center. The thin black lines also represent, unless otherwise noted, 8-bit data line connections. We'll be staring at this diagram for quite a while now and develop a good understanding of the Minimal 64x4 architecture. What I haven't shown in this diagram is the system clock. On today's layer 6 we won't bother ourselves with dynamics. Let us only say that all components are synchronized by a common clock. At the start of a clock cycle, outputs may put information onto the bus. At the end of a cycle, inputs may read this data from the bus. We have 5 functional blocks to cover. The Arithmetic and Logic Unit, ALU, a program counter, PC, a memory section featuring RAM, video RAM and flash, some I/O registers and the control logic. The A register can hold a single 8-bit data byte. Its input and output are connected to the data bus. If the control signal AI for A in is active, the register stores the bus value, and AO for A out puts the stored value onto the bus. Additionally, A forms a permanent input to the ALU. The B register works just the same as the A register. It uses the control signals BI and BO and permanently connects to the ALU as well. The ALU adds the values of A and B. The control signal EO puts this result onto the bus. ES, for subtract, inverts B prior to adding it to A. EC, for carry in, adds 1 to the result. This allows us to perform subtractions too, since in 2's complement, A minus B equals to A plus B inverted plus 1. Thus, in order to output A minus B, the control signals EO, ES and EC must be active simultaneously. Depending on its arithmetic result, the ALU sets 3 flags: the negative flag, the carry flag and a 0 flag. In addition to that, the ALU may output the result of a bitwise logical AND and a bitwise logical OR operation. This table here summarizes the ALU's functions and corresponding control signal combinations. An X denotes an active control signal and a minus sign denotes inactivity. The program counter consists of two 8-bit registers holding the most and least significant byte of a 16-bit memory address. The program counter points to the instruction in memory which is currently being processed. The counter can be incremented if CE for count enable is active. For writing and reading data to and from the register, 4 control signals are used. COL and COH for counter out low and counter out high, and CIL and CIH for counter in low and counter in high. Memory integrates a large number of byte register cells into a single IC. Each cell has a unique index or address. And to select a certain memory cell, the address bits have to be present at the address inputs of the memory chip. RO for memory out or RAM out will output the contents of the selected cell onto the bus. RI for memory in stores the bus value into the selected cell. The 16-bit memory address register, MAR, again consists of a most and a least significant byte. The MAR's output lines permanently define the address lines of the RAM and the flash chip. The two control signals MIL and MIH for memory address register input low and high read a value from the bus into either the LSB or MSB part. The control signal ME increments the current value held by the MAR. But there is a bit more to unpack here. The control signal MC switches the MAR input between the bus and the program counter via two 8-bit multiplexers. If MC is low, both MAR inputs will sample the current bus value. But if MC is high, the MAR's LSB will sample the program counter's LSB, while the MAR's MSB will sample the MSB. So by employing the control word MC, MIL, MIH, the full 16-bit program counter can be transferred to the MAR within a single clock cycle, while the bus can simultaneously be used for other data transfers. This feature improves the efficiency of the CPU pipeline quite significantly. The control signal MZ sets the MAR's MSB inputs to 0, while allowing for a simultaneous load of the LSB. This facilitates efficient access to the so-called zero-page memory range 0 to FF. The bank register controls whether RAM or a flash bank is active. NI for bank in reads the bus value into the bank register. In case the most significant bit of bank is high, flash memory is deactivated and RAM is active across the whole 64K address space. With the bank value ranging from 0 to 127, the lowest 4K of the address space exposes 1 out of 128 flash memory banks. Up here we have a seemingly unspectacular register that can drive each bus line to 5 volts, setting the bus to FF or -1. As we will discuss later, this register plays an interesting role in the more sophisticated operations the minimal 64x4 can perform. The 8-bit instruction register holds the opcode of the current instruction to be processed. II reads in a new opcode from the bus. A 4-bit step counter keeps track of the microstep of the current instruction. At the end of an instruction, this counter is reset to 0 with IC for instruction step clear. Upon FI, the state of the 3 ALU flags, negative, carry and 0, as well as the data ready flags of the UART and PS2 registers are being sampled. The step counter, together with the instruction and flag register, form a 17-bit address input to the 3 control ROMs. Each control ROM outputs 8 control signals, again shown in red, together forming a 24-bit wide control word. Now we know where all these control signals come from. The magic of a CPU stems from generating its own control signals while at the same time being controlled by them, by pressing its own buttons, if you will. Let us briefly discuss how an instruction gets executed on this hardware. Upon pressing the reset button, the program counter, the memory address and bank registers, and the step counter are set to 0. Now here is an important point. Regardless of the state of the flags register and instruction register every instruction starts with the same control word as microstep 0, also known as the instruction fetch cycle, ROIICEME. Let's break this down step by step. RO puts the content of the memory location defined by the MAR, which is currently 0, onto the bus. II transfers this value into the instruction register as the new opcode. CEME increments both the program counter and the memory address register by one step, so that the next instruction or possible instruction arguments become accessible. Since by now the instruction register knows its new instruction, steps 1 to 15 may vary for each instruction, as selected by the opcode inside the instruction register and the flags register. Each instruction consists of a unique sequence of up to 16 consecutive control words, the instruction microcode. The full microcode of the minimal 64x4 instruction set is defined by the files microcode.dev.csv and microcode.rom.csv in the project's repository. Let us take the time and analyze the microcode of three closely related instructions: LDI for load immediate byte into A, LDB for load byte from absolute address into A, and LDZ for load byte from 0 page into A. LDI has only two steps. Step 0 fetches the LDI opcode from memory, and step 1 loads the following immediate byte argument into the A register. With each step we also increment the program counter and the MAR with CE and ME control signals respectively, such that when IC resets the step counter at the end of the instruction, the MAR is already pointing to the next instruction in memory. LDB has a bit more to unpack. Step 0 again fetches the opcode. Step 1 reads the target address LSB into the B register. Step 2 reads the target address MSB into the MAR's MSB. And step 3 moves the content of B to the MAR's LSB. Note that the program counter doesn't remain in sync with the MAR here, since we pointed the MAR at the target memory address instead. And you might also be wondering why the target's LSB doesn't go directly to the MAR, but takes a little detour through the B register. Now that's because if we change the LSB of the memory address register right away, we wouldn't have been able to read the second part of the target argument anymore. In step 4, we finally load the data byte from the target memory location into A with ROAI. And we also need to set the MAR back to the next instruction to execute. Thankfully, this information isn't lost, but stored in the program counter. We only need to transfer it to the memory address register. We could use counter out low, memory in low, and as another step, counter out high, memory in high, and then pull the instruction step counter clear. But that would cost us 2 valuable clock cycles. As we already know, the minimal 64x4 can directly connect the 16-bit program counter to the MAR by pulling the control signal MC, thus completing the transfer in just a single cycle with MC, MIL, MIH. Since this doesn't even use the bus, it can happen in parallel to RAM out A in, all within step 4. In total, we are saving 2 cycles here, speeding up the instruction by almost 30%. Let us now see how 0-page addressing can add to that. LDZ has only 3 microsteps to cover. Step 0 is again our instruction fetch. In step 1, the argument, that is the 0-page address, is transferred into the LSB of the MAR via the bus by RAM out memory in low. Simultaneously, MZMIH disconnects the MAR's MSB inputs from the bus and instead shunts them to 0. Thus we are setting the full 16-bit 0-page address in just 1 cycle instead of 3, making LDZ about 40% faster than LDB. I know it's a lot of abbreviations here, but hopefully you are following along. The minimal 64x4 runs at a clock rate of 8 MHz, giving it an additional 30% speed advantage over its predecessor, the minimal 64. In total, the minimal 64x4 is therefore on average 100% faster than the minimal 64. Finally, let us not forget the I/O registers. The PS2 keyboard register as well as the UART receiver may output their current value onto the bus with the corresponding control signals KO for keyboard out or TO for terminal out respectively. The UART may also read the current bus value into its transmitter with TI for terminal register in. TO, KO and TI are not directly generated by the control ROM, but are derived logically from the signals MZ, AI, BI and AO as shown in the diagram. Congratulations! By now you are familiar with the minimal 64x4 architecture, but the real fun still lies ahead of us. Now that we have a firm grasp on how the CPU works, let's emulate it. The emulator's core will require only 80 lines of code. We'll be using JavaScript for portability, so you can run the emulator right in your browser. Now, if you are about to shout, hey, you've already done that a year ago, let me say, today's approach will be very different. We'll be emulating the CPU on microcode level, not just on instruction level. We'll be reading and using the actual microcode from the control ROMs of the CPU. Let's go! I am using the P5.js library and the P5 editor for convenience. We start by defining the RAM, flash and control ROM arrays. I have already uploaded the ROM and flash images into my project here. Next we represent the CPU state with all its registers. And now we define all the control signals. Note that some of them act active low. We convert them all to active high with this invert mask. And let me also define our 5 flag lines and preload the binary image files. In Setup, we create our canvas, build the flash array and stitch together the 3 control ROM images to form a single 20-bit wide control word array. Our draw function will also be pretty simple. Update VGA will project the video RAM area of the minimal onto the canvas. Then we use the inverse of the frame rate variable to determine the frame time and simulate the appropriate number of 125 nanoseconds clock cycles, and we are done. Well, not yet. We still have to write the 2 functions, update VGA and do clock here. Here is update VGA. I generate a 512 by 256 pixel image and request access to its pixel data array with index P into it. Then we loop through the video RAM area of the minimal 64x4, fetch a byte, and for each of its 8 bits we set the appropriate image pixel either to bright or dark. Let's test that real quick by randomizing the RAM content. Okay, that is working. Now let us tackle the actual CPU emulation. We begin by fetching the current control word from the control ROM, with the flag register, instruction register and step counter forming a 17-bit wide index. The ALU calculates the sum of the registers A and B with a possible negation and carry in. Depending on the result, we also set the carry, 0 and negative flag lines. Now let us implement the outputs to the bus. We just check whether a specific control signal, let's say A out, is active, and if so, we output the register's content to the bus. The ALU's output and logic section is also pretty straightforward. EO puts the result onto the bus, but if EO is off, ES and EC activate the logical AND or the logical OR section. For RAM out, we distinguish between RAM and flash access as determined by the MARs and the bank register's most significant bit. That leaves us with the inputs. The only control signal that we need to invest a bit of work into is RAM in, since again it depends on the MAR and the bank register whether we write to RAM or flash. A RAM write is easy. But if we write to flash, there is some internal state of the flash IC to model here, according to the datasheet. We calculate the actual flash address first. Only the lower 12 bits of the MAR and the lower 7 bits of the bank register are connected to the flash address lines. And with this switch statement, I model the write procedure and the sector erase procedure as described in the datasheet. For the remaining inputs, things are very straightforward. Only the inputs of the MAR require some additional attention here, since it depends on the control signal MC, whether these inputs connect to the program counter or the bus. The MSB of the memory address register can also be set to 0 by MZ for fast zero-page access. The only thing missing now is the step counter reset by IC, which also models a possible 4-bit wraparound. And that's it, we are done. The Minimal should be able to boot now. Let's click the play button. Yeah, and it does. You might have noticed that I've omitted the UART and the PS2 interface. This part isn't very informative and quite boring to watch. Here is my full code that includes everything. The link to both versions is of course in the description. Let us see if everything is working as it should. Yeah, and looks and feels just like the real hardware. I've also implemented a feature to upload some code into the emulator. You can post hex data as generated by the Minimal assembler into this file uart.txt. I have pasted some code displaying the Mandelbrot set, for example. Let's start the receive program on the Minimal, and by typing F2 we feed this file as UART input into the Minimal 64x4. Alright, we have transferred the data into the RAM now. Let's run the code by typing run 2000, and that's working very nicely. So if you are still with me, you have deepened your understanding of the Minimal 64x4 by emulating it almost down to the hardware level. What do you think of the Minimal 64x4's microcode running right in your browser? Let me know in the comments. Take care. Bye.